Dear learners, today we are going to see the unit number 4, Interprocess Communication and Synchronization from the operating system. After going through this unit, you should be able to understand the importance of interprocess communication and synchronization, understand the use of semaphores in interprocess communication and synchronization, and solve the classical problems in concurrent programming. An important and fundamental feature in modern operating system is concurrent execution of the processes. This feature is essential for multi-programming, multiprocessing, distributed systems, and client-server architecture. In this discussion, we will look at the various design issues, problems, and the wide variety of solutions available. Generally, there are three forms of interprocess interactions. First one is interprocess synchronization. Set of protocols and mechanisms used to preserve system integrity and consistency when concurrent processes share that are usable. Interprocess signaling, the exchange of timing signals among the concurrent processes used to coordinate their collective progress. And the last one is interprocess communication. Concurrent cooperating processes must communicate for data exchange, reporting progress, and accumulating collective results. In the multiprocess application, there are various degrees of instructions. First one is the competing processes. Processes themselves do not share anything, but operating system has shared the system resources among these processes, competing for system resources such as disk, file, or printer. Cooperating processes. Result of one or more processes may be needed for the another process. Cooperating process, cooperation by sharing. Example, sharing of an input-output buffer. Example, concept of a critical section. Cooperation by communication. Example, typically no data sharing, but coordination through synchronization becomes essential in certain applications. Among the three kinds of interactions indicated by 1, 2, 3 above. First is at the system level. Potential problem is a deadlock and derivation. Second is at the process level, significant problem in the realizing mutual exclusion. And third is more synchronization problem. We'll study mutual exclusion and synchronization here, and thereafter deadlock and derivation for the later time. First, we have to understand race condition, the situation when several processes access and manipulate the shared data concurrently. The final value of the shared data depends upon which process finishes last. To prevent race conditions, concurrent processes must be synchronized. Mutual exclusion problem. Successful use of concurrency among the processes requires the ability to define the critical sections and impose the mutual exclusion. Critical section is a part of the process code that affects the shared resources. Mutual exclusion in the use of the shared resources is provided by making its access mutual exclusive among the processes that share the resources. And this is known as a critical section problem. Any facility that provides the mutual exclusion shows meet these requirements. No assumption regarding the relative speed of the process. A process in its critical section for the finite time only. Only one process allocated in the critical section. Processes requesting access to the critical section should not wait indefinitely. A process waiting to enter critical section cannot be blocking a process in a critical section or any other process. There are various algorithms of it. The first algorithm is there, that is program 1. That is algorithm is given here to process 1 and process 2. So process 1 is there, begin while to do, begin while turn equal to process 2, do, keep testing, critical section, turn, okay, process 2, other P1 processing, end while end P1. Process P2, begin while to do, begin while turn equal to process 1, do keep testing, critical section, turn equal to process 1, other P2 processing, end while end P2. Parent process, begin mutex 1, turn equal to, you have to set, initiate P1 and P2, end mutex. There are 4 major drawbacks in this algorithm. When one process is in critical section, other processes consume the system resources doing busy waiting. Compulsory turn taking takes place here, P1, P2, P1, P2. Independence on the other processes to enter into the critical section because P1 set the turn for the P2 and P2 set the turn for P1. If any process crashes outside the critical section, crash processes is unable to set the turn for the other processes, results in the deadlock. To overcome the disadvantages of the first algorithm, we have another algorithm, that is algorithm number 2. To process P1 begin while to do begin while process P2 using do keep testing. P1 is equal to true. Critical section P1 using is equal to false. Other P1 processing end while end P1. Process P2 begin while to do begin while process P1 P1 using do keep testing. P2 using true. Critical section P2 using false. Other P2 processing end while end P2. Parent process P1 is equal to false, P2 is equal to false, initiate P1 and P2, and the end notice. This algorithm has one problem. If both the processes are outside the critical section and both flags are indicating resource is free, and if both processes enter their critical section at the same time, resource will not be allocated any of this process and system will enter in a problem. To avoid that, we have the algorithm number 3. To process P1 using is equal to true, while P2 using do keep testing. Critical section P1 using is equal to false. Other P1 using end while end P1. Process P2 begin while to do begin. Process P2 using is equal to true, while P1 using do keep testing. Critical section P2 using is equal to false. Other P2 processing end while end P2. Parent process begin text P1 is equal using equal to false, P2 is equal to false, initiate P1, P2, end notice. This is quiz time. Interprocess synchronization is a set of dash used to preserve system integrity and consistency when concurrent processes share that are used. When two or more processes are accessing common address space for the reading and writing, and the final result depends upon who runs precisely is called dash. No other process enter critical section unless process which is in dash completes the task and come out of the critical section. No assumption about the relative dash of the process. A process requesting its critical section is not allowed to dash a process which is in critical section or any other process. Answers: interprocess synchronization is a set of protocols and mechanisms used to preserve the system integrity and consistency when the concurrent processes share that are used. When two or more processes are accessing common address space for reading and writing, and the final result depends on who run precisely, is called race condition. No other process enters critical section unless the process which is in critical section complete its task and come out. No assumption about the relative speed of the process. A process requesting its critical section is not allowed to block a process which is in the critical section or any other processes. These are the references. Thank you very much. We'll stop it here today.